All right, so far we've dealt with the Green's theorem. Let's see if you remember what a Green's theorem is. It's the integral of what? If I have L and M two functions, it's a two-dimensional vector field. The dr over the boundary of a domain counterclockwise. What did this integral represent? Do you remember? No. Curl is on the right side. What was this? Somebody said it.
Straight path.
No. Circulation of a vector field. So if this is the vector field, if you want the circulation of the vector field around some region D, you calculate this. Right? And Green's theorem says because the density of the circulation is the curl, which is the following form: partial x, partial y, Ln. If you multiply by dA, what does that mean? If you have this domain D, you can cut this into very, very fine pieces. Now, on this very, very tiny piece, if you multiply this area of this piece times the density of the circulation, this quantity gives you the circulation around this very tiny piece. And I explained that because the circulation is additive, it has this additive property. If you add the circulation up on these small pieces on the entire domain, if you add them up over the entire domain D, you end up with the circulation around the domain D. That was basically the proof of the Green's theorem that I showed you. It looks like even with my best efforts, a lot of you don't remember the Green's theorem, nor understand what it means. So here's the question I want you to try. Well, I'll show you, and maybe if we have time, I'll give you some time to try the next one. Okay? So what I want you to do is verify the Green's theorem for vector f equals to 3y, 5x on the domain x squared plus y squared less or equal to 9. So let's try this. I explained that Green's theorem is useful when one side is easier than the other, because if you had a line integral question, which is hard to do, you can use the fact that it's equal to this, and if this was relatively easy, we can use this result to figure this out, right? Or vice versa. Sometimes this is easier, and you can figure this integral out by computing this one. However, for this question, it said verify. Therefore, I want to know that indeed the left side and the right side gives you the same value. So this question asks you to compute this left side. It asks you to compute the right side. And after computing those two separately, by looking at the values, you can deduce that they're indeed the same. That's the goal of this problem. So when you see this word verify, that means you have to compute both. Let's try it. Okay, let's start with the left side. What is this domain? Can you tell me what kind of domain this is? It's a circle of radius? 3. So it's the domain described by this inequality is the interior of the circle of radius 3, this disk. And then what is this boundary of D? The domain is the disk and the boundary is the circle. Yeah, boundary is the circle. And you have to parameterize this circle counterclockwise because the integral has to be done counterclockwise. Right? So if we do this calculation, if we parameterize this counterclockwise, what is the formula for RT? Because, I mean, to calculate this, you have to divide by dt and multiply by dt, and you can't do the calculation without knowing what R of t is, right? So that should be the very first step. You have to figure out what R of t is. Can you tell me how to parameterize this circle?
All for x, all for y.
How? No. Do you remember how to parameterize the unit circle? Okay, hint. Unit circle is parameterized as cosine t comma sine t. You remember that, right? Okay, now how is this one parameterized? 3 cosine t, 3 sine t. Because it's just 3 times the unit circle. Unit circle is radius 1, you just multiply by 3. The only thing you have to be careful is this counterclockwise? Right? It starts from here, goes like that, right? Okay, and then what will be the t value to make it go around the full circle? 0 to pi. Because t acts like the angle. That's your RT. And if you know that RT, now you're ready to calculate. So let's calculate. You're trying to calculate around this circle with this vector 3y comma 5x. So this is your L, that's your M. Dot it with dr. But in order to calculate, what's the first step? You divide by dt. That's the most important step, right? Because once you remember that, then everything else falls into place. Okay, so we did that. Now, this has to be evaluated on the curve. So what do? Think about this as x t. You think about this as y t. Right? So your y should be replaced by 3 sine t, whereas your x should be replaced by 3 cosine t. All right, so let's do that. Let's continue to calculate. That's 3 times 3 sine t, comma, 5 times what? 3 cosine t. That's 5 times x. X is 3 cosine t. Dotted with now we have to calculate this, right? dr dt. What's dr dt? Huh?
Negative 3 sine t.
And then?
3 cos t.
And t goes from where to where? All right, so that's what you have to calculate. And it's almost done. It's not that hard now. 3 times 3 is 9. 9 sine t times negative 3, that's negative 27 sine squared t. Okay, and then 5 times 3 times 3, that's 45 cosine squared of t. Now we learned about how to calculate the integral of sine squared and cosine squared. It involved using the following identity. That sine squared is 1 minus cosine 2t, whereas cosine squared is 1 plus cosine 2t. Let's continue this. So it will be negative 27 plus 45 over 2. And negative 27, positive 27 cosine t, 2t, and plus 45 cosine 2t over 2, 0 to pi. Let's see, what's this? 18 divided by 2 is 9. And then 27 plus 45 is 72 over 2, that's 36. Cosine 2t, 0 to pi, t, which is 9t plus 18 sine 2t. Why did 36 turn into 18?
Divide by 1/2.
Because of this 2, you have to divide by this number, right? So you have to divide 36 by 2 because of this number. If it was 3, then you have to divide by 3. The reciprocal of this number comes up front. And then you have to plug in 0 and 2 pi. 2 pi goes in here, which is 2 pi times 9 is 18 pi. And then in both cases, when you plug in 2 pi, sine 4 pi is 0. When you plug in 0, sine 0 is 0. Plug in 0 is 0. So this is the only value that you get. So 18 pi is your answer. Are we done? That's the answer? Yeah?
No, we have to do both.
No. You have to do both. So what do we have to do next? The right side. Right? This side. So let's calculate that. Okay, first of all, what is round x, round y applied to 3y, 5x? Well, this is what we call a determinant, which is AD minus BC. So you do this times this minus this times that. If I write it down, that means partial with respect to x hits 5x minus partial with respect to y hits 3y. It's going to partial. If you differentiate 5x by x, you get 5. If you differentiate 3y by y, you get 3. So you get 2. And then you're trying to integrate on this circle 2 dA. Right? Since this thing here is 2, I now have this. All right, let me just write it out. This is equal to integral of 2 dA, and 2 can be pulled out, right? Now, what do you get if you integrate 1 over origin? What does this give you?
R squared.
What does this give you? If you integrate 1 over any region, it gives you?
Here.
It gives you the area, right? It gives you the area of the domain. What's the area of the circle? Pi r squared, right? 3 squared is 9. 9 pi times 2 is? 18 pi. So what? What did we achieve? We verified that two sides are equal, right?